Hello, hello. It's Mr. Canfield. We're going to be doing the AP Calculus Function Analysis Worksheet. Woo! Ignore the fact that it says something else here. I scribbled it out and I wrote name over here. I clearly made this from scratch. All work must be shown in this course for full credit. I didn't take this from a college website. What are you talking about? All right. Complete each statement with the correct word. So what I'm going to do is I'm going to read this. I'm going to think about it. I'm going to give a hint, and then I'm going to give the answer. So I would say try to stay ahead of me and think about what you want to write for the answer before I write mine. There are correct answers for these. When f prime is blank, the graph of f is increasing. So an f prime, so that's the slope of f. So what kind of slope would give us an increasing f? And that would be positive. So hopefully then it follows when f prime is negative, the graph of f is decreasing. All right, the next one talks about f double prime. It says when f double prime is blank, the graph of f is concave upward. So hopefully that's simple enough. When f double prime is positive, we have concave up, and negative gives us concave down. When f prime is blank, the graph of f is concave upward. Okay, so we need to think about this. F prime, but f prime doesn't tell me concave up or concave down. That's f double prime. Well, how is f double prime related to f prime? F double prime is the derivative or the slope of f prime. So if f prime, let's see, we need concave up. That means that we need f double prime to be positive. Or otherwise put, the slope of f prime needs to be positive. So if the slope of this is positive, then we would say that f prime is increasing. And similarly, f prime, if it was decreasing, then it would have a negative slope, and a negative slope would mean a negative derivative, or a negative f double prime. So it's decreasing. Kind of weird stuff to think about, for these last two especially. So use the function 3x minus x cubed plus 5. Where's the function increasing, decreasing, concave up, concave down? All right, and it says justify for each of these. So I'm going to make sure that I include correct language to help you all see it. So first things first, increasing and decreasing, we need y prime. So let's see, y prime is equal to 3 minus 3x squared. And that's it. Oh, okay. So I can set this equal to 0, and I can solve it. And you can solve it any way you want. You can factor and get your difference of squares out of there. I'm going to add the 3x squared to both sides, and then divide both sides by 3. And I get x squared is equal to 1, so I get x is equal to plus or minus 1. And then I'm going to do my sign chart analysis. So 3 minus 3x squared, I'm just going to I don't have mine factored, so I'm just going to deal with that. So less than negative 1, so that'd be like negative 2 and so on. A negative squared is still a positive, and then those subtract. We wind up getting a negative still. We get a 0 here, we get a 0 here. In between, like if I plugged in 0, I'd get a positive, and then anything after, we get another negative. So that's what I got for those. So then that tells me the function is increasing. This is f prime, right? So f prime is positive here, so it's increasing from negative 1 to 1. And I could say, because if you wrote BC on my paper in class, I wouldn't be upset. I know what you mean. You're not going to lose points for that. On the AP exam, I would take the extra 5 seconds and write full words instead of abbreviations. Because f prime is positive, which I can write f prime is greater than 0. So it's increasing on -1 to 1 because f prime is greater than 0 on that interval. And likewise, we can say f prime is less than 0 on, let's see, -infinity all the way up to -1, and then 1 all the way to infinity. So f is decreasing there. Okay. Where's the function concave up? Oh, okay, so I need second derivative now. So second derivative, here was y prime. Let me find y double prime. Was that -6x? Interesting. So I'm going to bring in another color now just to kind of make sure things are nice and clear. So here's f double prime. F double prime, let me just make sure I didn't make a silly mistake. So that's 3 minus 3x squared, and then the 3 goes away, and then -3 is 6. Yeah, okay. So now I can, if I want, I can kind of add to my sign chart here. I can add information about the f double prime, and I know I bring in a possible inflection point when x is, oh, I didn't solve this. Got a little bit ahead of myself. We can solve that and get x is equal to 0. So in here, these are still all positives for f prime, but now I can think about f double prime as well. So negative numbers, I plug them in and I get positives, 0, and then positives I plug in and I get negatives. So we wind up being concave up, inflection point, concave down. So I can say, similar to the previous ones, I can say it's concave up on -infinity to 0 because f double prime is less than, greater than 0. And, you know, very similar, we can say concave down on 0 to infinity because f double prime is less than 0. Points of inflection. So we have an inflection point when x is equal to 0. And just in case, they might be looking for the x comma y version. So I've seen inflection point be just the x value. I've seen inflection point be the x and y value. People mean different things. And this is a big argument for why we need convention in mathematics. We want one word to mean the same thing for everybody. That's why, you know, we try to use PEMDAS everywhere. Everyone uses order of operations the same way. That's what we're going for. So I'm actually going to try to get the point 0, comma, I'm going to go back here, plug it in, I get 0, 0, I get 5, okay. So find all extrema and justify your response. I'm going to talk through the justification. You know, maybe I'll write it. Okay, so let's see. Ooh, especially because it's gonna ask me to create a sketch in a moment. So now that I have the XY point there, we'll get the XY point of our extrema. So if we go back here, we remember that, you know, f prime being negative means the slope is negative, slope is positive. So we have a dip here. We know that that's a minimum, and then we can ignore the f double prime stuff. And then we have a maximum because it's going up and then comes back down. So we know we have a minimum at, so a relative minimum at -1 comma something, and a relative max at 1 comma something. And I'll just find these by plugging them back into the original, right? So 3 times -1 minus -1 cubed plus 5. Let's see, that turns into a positive 1, a -3. So -3 plus 1 plus 5, so 6 of 3. All right, and then the relative max hopefully will be above the relative min. So I plug in I'm just going to kind of do this in my head because the x's all turned to 1. So 3 minus 1 is 2, plus 5 is 7. All right. So I actually have 3 points now. Oh, I'm supposed to justify this. Okay, so here's my justification. It's a relative min because there's a lot of things that we could say. So because f prime of x changes, remember the only way we can have a min or a max is with a sign change in f prime. F prime changes from negative to positive. At x equals -1. And we can call this a relative maximum because f prime changes from positive to negative at x equals 1. So there are both of our justifications for that. So now if I was going to create a sketch, I actually have enough information to draw a pretty good sketch of this. I have a relative min at -1, 1, 2, 3, 4, 5, 6, 7, -1, 3. I have an inflection point at 0, 5, 1, 2, 3, 4, 5. And then I have a relative max at 7, 1, 7. So if I look at this, I've got a negative slope coming in all the way till I hit this, and I'm concave up. So concave up, this is my only relative min, so I know then it's got to do something like whee, right? Concave up. And then switches here to concave down, which doesn't mean a whole, like we don't need to worry too much about that, but there, look at now, and then that's a max, and then whee. Now, I don't know where the zeros are of this. I haven't gone in and calculated them, so I don't know where this touches the x-axis. I'm not super worried about that, but this is a general sketch of that. So we're going to keep going. Let me see if this kind of bleeds through too much. It doesn't appear to. Oh, sorry if that noise was super loud. Just realized my pop socket was open. Find all local extrema of the function and justify your response using the second derivative test. So we have not talked about this. Allow me to show you. So second derivative test is pretty nice. Check it out. If we take the derivative of this, we get -6x squared plus 12x. And we can find, so we're looking for local extrema or relative extrema, relative maxes and mins. So we'll set it equal to 0 like we normally do. -6x squared plus 12 is equal to 0, oh, 12x. So they both have x's, so I'll factor. I see a lot of you try to solve this by adding things to the other side. If there's more than one variable, like if it's x squared and x, there's more than one term with the variable and you try to move it, you're reaching an unsolvable situation or a situation where you're going to lose answers. Instead, we want to set it equal to 0 and try to do some sort of factoring. So I'm going to factor a 6 and an x out and get -x plus 2. And when I solve these individually, I get x is equal to 0 and x is equal to 2. So here's the cool thing. I don't need to do a sign chart if instead y double prime -12x plus 12. So I won't pause really quick and think about this. 0. It's either a min or a max. Or maybe it's neither. And so what we're going to do is we're going to see, hey, what kind of concavity do we have? Think about the concavity of a max or a min. Here's what a max looks like. What concavity is that? So what does that tell us about f double prime? Oh, f double prime needs to be negative here. If it was going to be a minimum, then that means that it's concave up, and that means that f double prime has to be greater than 0. So we can actually, without doing a sign chart, I can say, hey, What's f double prime, or I guess y double prime? Y double prime when x is equal to 0. Well, let's see. I get negative 12 times 0 plus 12. I get a positive number. It's concave up, and so that tells me that 0 is a relative min. It has to be. Now you may be thinking, now there's other situations, Canfield, though. There are these things that we don't have a good name for in 2D, and you've called them saddle points before, but this kind of thing. Here's the thing. See this right here? This is concave down. This is concave up. What does that make this? This is an inflection point. This means that f double prime will equal 0 here. So if it's not negative or positive and it winds up being 0 or undefined for that matter, because there are other things, like you can have a strange, turns out when it's like this, then the second derivative might be undefined. So it's still going to be an inflection point though. So I know that's a relative min because f double prime of 0 is greater than 0. Similarly for this one, if I plug 2 into my second derivative, I get negative 24 plus 12. I get a negative number. A negative number. That means it's a frowny face. There, now they're faces. So because of that, we know this is a relative max because f double prime of, not 0, of 2 is greater than 0. Oop, less than 0. Wow, I just got all that backwards. Okay. Is a negative number is less than 0. And you could say, meaning concave up, meaning concave down. All right. Determine the intervals on which the graph of each function is concave up or concave down, and determine all points of inflection. Justify your responses. And you might look at this first one and go, no thanks. This is actually really nice. Promise. All right, so we're looking for concavity stuff. So y prime, we need y double prime, but we'll do 5 times 1/20th. That's 5 over 20, which is 1/4. Next to the fourth, plus x cubed minus 9 over 2x squared minus 27x plus 1. You might now see why these fractions were there. Let's do the next one. Y double prime is equal to x cubed plus 3x squared minus 9x minus 27. Not so bad. So if I'm trying to set this equal to 0 and find inflection points, all right, so we're going to do factoring by grouping. It's a good old strategy. Whenever we've got 4 terms, that tends to be a factoring by grouping strategy. So I can take an x squared out of the first 2 terms, be left with an x plus 3. So I'm hoping that I can pull something out of the second 2 terms to make a matching parentheses. And sure enough, I can pull a negative 9 out of this second group and get x plus 3 again. And then we can factor the x plus 3 out of both, like that group and that group, and get x plus 3 outside of x squared minus 9. Oh, x squared minus 9 factors. So I get 0 is equal to x plus 3 times x plus 3 times x minus 3. So my inflection points wind up being negative 3 again, and 3. So we only read it once, but yeah, I'm not gonna have enough room over here for you, am I? Rats. This is gonna be one of those situations that does one of those things and has a non-existent slope, which makes an inflection point still. All right, so go do the table. I'm not going to do the arguments anymore. We did the arguments on the first page, and unless you personally feel the need to do them over and over again, I think the point has been made. So we get negative 3, we have 3. This is interesting. We have x plus 3 oh, whoops, put in the wrong spot. X plus 3, another x plus 3, and then an x minus 3. So let's see what happens with these. So less than negative 3, like negative 4, we do get a negative here, then a 0, and the rest are going to be positive. This one, same thing. We start out with negative, get a 0, the rest are going to be positive. This one, we have a negative, and then negative 3 minus 3 is still negative. More negatives, 0, now positives. So what is f double prime? Let's see, I have negative, 0, negative, 0, positive. So this one's going to be concave down from negative infinity up to negative 3. It's not either way at negative 3. And then from negative 3 to 3. It's going to be concave up from 3 to infinity. All right. Yeah, we're going to skip that one. No, come on. So y prime is equal to 2/5 times x to the negative 4/5. And then y double prime is going to be gross. We get negative 8 over 25 x to the negative 9/5. So our inflection point for this will be 0 because that drops to the bottom. You know what? Just so I'm a little pressed for time. I don't know if you can tell by the way I'm speeding through this. I really don't like having to miss a day with you guys, but I can write this as x to the 9/5 down here. And so we're trying to make this equal 0. Well, the numerator never equals 0, so it doesn't. The bottom can equal 0, and that'll make negative 8 over 0, which is, oh no, I can't do that. Makes an undefined situation. So that's going to be our inflection point, potentially. Notice how the original function, you can plug in 0 and we're fine. So here's x, here's f double prime. So when I plug in a negative for f double prime, a negative to the 9/5, since they're both odd, it's going to stay whatever sign it was, because a negative times a negative times a negative 9 times is still negative. And the square roots and cube roots and stuff work the same way, just in reverse. So odds preserve the signage. So if I plug in a negative, the bottom's going to be a negative. So a negative divided by a negative is a positive. 0 is going to be DNE, and then up here it's going to be negative. You plug in a positive, you get a positive. Negative divided by a positive is a negative. So, so the point of inflection is going to happen at 0. We can plug it in here and we get 0, 3. And if you look at the graph of this, you should be able to see kind of the oddity that is this. Woo! Sorry if I made you yawn. Some of my students have been yawning today and it's been making me yawn. All right, so I typed it into my calculator and you can see this weird little jump here, but I promise you, I'm going to turn the axes off just so you can see really clearly. It doesn't disappear. There's not like an undefined portion in there, but there is a place in there where the derivative is undefined because it's vertical for a moment, and the second derivative is undefined for a moment, but that's fine. I'm not talking like dog in a house that's on fire smiling at the camera like in that little cartoon. This is fine. I really do mean this is fine. Okay, well, I'm glad I did that. So let's say see video around 22-ish minutes. So I'll timestamp that. I'm planning on scanning this so you guys can have it. All right, if f is continuous on 0, 3 and satisfies these things, find the absolute extrema on f and where they occur. I love this. Okay. Absolute extrema. Absolute, no longer talking about relative. So relative extrema, we could definitely say, let's see, it's going up, stop, coming down, weird, going back down. So we could say that this is a relative max. But we want to find the absolute maximums. and minimums. So let's look at our y values. We have a 0, a 2, a 0, and a -2. So with our 0 and our 2 and our 0 and our -2, what was I saying? All right, so with the 2 and the -2, they are likely the highest and lowest we get on this. The one thing I want to think about is there any way for me to get higher than 2? And so if we think about the slope, well, the slope says we're going up, going up, going up. We hit 2, then the slope says going down, going down, going down, and we're going down for the rest of it. So no, the highest we ever get is 2. So you can say the max is equal to 2. And then the lowest it ever gets, let's see, can it possibly get lower than -2? So starts out at 0, right? So our initial y value is 0. And then the slope says we're going up, we're going up, we're going up, we're going up. We hit the 2. Do we keep going up after that? Let's see. No, we go down, have this weird 0 here, keep going down, keep going down. So, nope. It's been going down, going down, going down. -3 is the lowest we can possibly hit. So that's the idea of an absolute max or an absolute minimum. So points of inflection, let's see. Do we have any places where the sign changes on f double prime? And no, it's always negative or 0. So that's going to be a situation where we could have a concave down, flattens out for a second, then keeps on being concave down, keeps on being concave down, keeps on being concave down. So we're not going to run into any inflection points. So, womp womp. So sketch the graph. Well, we'll start out with the y values. So here's 0, then 1, then 2, then 3. So we're at 0, 0. We're at 1, 2. We're at 2, 0. And we're at 3, -2. So I can't just connect them like with straight lines. I do need to think, okay, what's my concavity? It is concave down here. And when x equals 1, I do have a maximum, so that's good. Then I still go down, and here's the part that like it's still concave down. So how could I have a derivative that doesn't exist? Oh, you know what? I could have it like this. It could be like swoop, go down, and then go down. Something weird like that. That's a strange thing happening there because the derivative doesn't exist there, but it's concave down on both sides of it. So, oh dear, I just ran off the screen. I'm so sorry. So, concave down, and then maybe like an extreme, like some weird little things happening there. Sorry to leave you in the dark. All right, let's keep going. Let f be a function that is continuous on the interval 0 to 4. The function f is twice differentiable. Twice differentiable. That means that we can find f prime and f double prime. Except at x equals 2. Oh, right. See how it's not differentiable at x equals 2? The function f and its derivative have the properties indicated in the table below, where d and e indicates that the derivatives of f do not exist at x equals 2. So, yeah, describe the behavior of f of x in each interval using the information above. So from 0 to 1, let's see, from 0 to 1, the y values are underneath the x-axis, the slope is positive, and it's concave down. So we could say f of x is increasing, and we could say that it's concave down. From 1 to 2, its slope is still positive, and the concavity is positive, so it's increasing, and it's concave up. From 2 to 3, Slope is negative, and so is concavity, so we can say it's decreasing, and it's concave down. It's still decreasing, and then f double prime is positive, so concave up. Decreasing, and concave up. For 0 to 4, find all values of x at which f has a relative extremum, max or min. Determine whether f has a relative max or relative min at each of these values. Justify your answer. So let's see. Or we can kind of tell that from f prime on its own. So 1, we have positive and positive. Oh. So that wouldn't be a relative extreme. It's going up, stops, keeps going up. So here we have positive to negative though. So 2, when x is equal to 2, is going to be a relative positive to negative, so relative max. So the problem is we can't use our second derivative test because the second derivative isn't defined here, so I'm not able to say if it's its concavity tells us what's going on. But so I guess I was wrong earlier when I was talking about how we can handle that. Anyway, in this situation, since f prime goes from positive to negative at x equals 2, that's how we know. So relative max, because f prime changes from positive to negative at x equals 2. And so we could even say the point, but this one is very clear. It says, find all values of x for which f has a relative max or min. So it's not asking for the x and y value. So on the axes provided, sketch a graph of the function that has all the characteristics of f. So let's see, 0, negative 1, that's easy. 1, 0, still easy. 2, 2. 3, 0. So it's increasing and concave down, so I need to make sure I have a concave down kind of shape. Increasing and concave up, I need to make sure I have a concave up. You know what? This is probably too small to see. So let's just zoom in just a little bit. So let's go here, 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 here. So increasing but concave down, so it's got to have that downward shape. Increasing and concave up, it's got to have that upwards kind of shape. Now, at 2, it's supposed to be DNE, which means we're going to have some kind of cusp point. After this, right, from 2 to 3, oh, did I mess it up? From 0 to 1, it's increasing and concave down. From 1 to 2, it's increasing and concave up. From 2 to 3, it's decreasing and concave down. Oh, we just don't have a y value after 4. We don't have a y value at 4. And then it's decreasing and concave up, so it's going to be some kind of like that. Like a shark fin, almost. All right. Calculator required. Let's see. Let's make sure we give ourselves enough room. All right. How much more is left? Cool. Yeah. All right. Let f be a function defined for x is greater than or equal to 0 with f of 0 equals 5. F prime, the first derivative of f given by the graph of f prime. Oh, this is the graph of f prime. Okay, I was like, f of 0 equals 5. I'm confused Because if f of 0 is 5, then this is the graph of f prime. Remember, each one of these y values is the slope at any given point. So, hey, when x is 1, what did the radar gun get when it clicked on f? Remember, these y values are showing us what the current rate was. So use the graph of f prime to determine whether the graph of f is concave up, concave down, or neither from 1.7 to 1.9. So I'm assuming 1.9 is going to be somewhere around here. Here's 1.7. Hey, what's the slope? The slope is negative, right? So slope, wait, no, we need to use fancy language. We need to say, since f prime is decreasing on 1.7, 1.9, f double prime. Oops. Okay, yeah, f double prime is less than 0, meaning f is concave down. Write an equation. Write an equation for the tangent line to the graph of f at the point 2, 5.623. So this is why we needed our calculator. Okay, so we know that we're going to say y minus 5.623 because it's a tangent line. Then there's going to be our slope, and then it's going to be x minus 2. No big deal. And if we want to find the slope, well, hey, we have f prime, right? So let's say e to the negative 1/2, right? Because 2 divided by 4 is 1/2, times sine of 4, which is 2 squared, to negative 0.459. Remember, if you don't do those 3 decimal places, you're wrong. Don't care how right you are, you're wrong. Unless you write the exact answer. Maybe your TI-89 spat out the exact answer. All right, back to no calculator allowed. All right, classic shapes. So this is some of the most challenging stuff for people right here, like just wrapping our heads around what's happening. So I really wanted to make sure we got to do this. So here we go. Let f be a function defined on the closed interval from -3 to 4 with f of 0 equals 3. The graph of f prime, the derivative of f, consists of one line segment and a semicircle as shown below. On what intervals, if any, is f increasing, decreasing? Justify your answer. So this is the graph of f prime. We did this before. It might actually help you if you go in and you say, okay, well, let me make a sign chart then. When does f prime equal 0, or when does f prime undefined? Let's see, f prime equals 0 at 2 and at -2. There are no open circles, there are no asymptotes, so those are my only zeros. So what's the value of f prime less than -2? Less than -2, the values of f prime are all positive. They're all positive y values here, so it's positive. At -2, it's 0. In between -2 and 2, all these y values are negative. And then 2, it's 0 again. And then after 2, it's negative again. So now I can see very clearly from my table, this tells me that f of x is going up, flat, down, flat, down. So I'm able to say that increasing, and we're not going to justify anymore, we justified on the first page. It's increasing from negative, oh, I was going to say negative infinity, but look at that. It starts at -3. From -3 all the way up until 2. I mean, -2, right? Increasing, stop. And then it's decreasing for the rest of it, except at x equals 2. So we'd say -2 to 2, and then 2 until 4. So that's that. Find all values of x for which f assumes a relative max. Well, you know what happens when we assume. No, just kidding. So a relative max. Based on this sign chart that we just did, it goes up, then it comes down. We should have a relative max at x equals -2. And I said I wasn't going to justify, but let me just justify in case. because f prime changes from positive to negative at x equals -2. Where's the graph of f concave up? Now, this is a little bit trickier. Remember, that comes down to f prime. Well, f prime, concave up and down. That's f double prime equals the slope of f prime. So the slope of f prime is going to tell us what f double prime is doing. What's the slope here? Negative. What's the slope here? Positive, then negative again. So we can go in and we can do a sign chart here. So f double prime, we can say f double prime is negative, then does not exist because the slope doesn't exist right there. That's a weird point. Then positive, then slope is 0, then negative. And so I'm able to say it's concave up between -2 and 2, and concave down from -3 to -2, and then 2 to 4. All right, next. Find the x-coordinate of each point of inflection of the graph of f on the open interval. So, inflection points are when the sign changes and we have a 0 or DNE. So that's at -2 and at 2. So when we say because f double prime changes sign. So those are inflection points. I wrote inf points, whatever. Inflection points, x is equal to 2 and x equals 2, because f double prime changes sign at those values. Find an equation for the line tangent to the graph of f at the point 0, 3. Remember, we just need f prime of 0 then. Hey, what's f prime of 0? We can go up here, and when x is 0, f prime is at -2. So I can simply write y minus 3 is equal to -2 times x minus 0. Sketch a possible graph of f. Okay, we're going to have to be a little careful here. Oh, hey, look at this. We do know f of 0 is equal to 3. So I know that f of 0 is 3. And then I know that it's going up. Oh, wait, no. 1, 2, 3. I know that it's going up until we hit -2, where it has a maximum. And then it's going to be basically falling for the rest of it. So my maximum is most likely going to be above this 3 in order for it to be falling after that. So I'm going to say my max is up here. So I don't know how low it starts, but I can be like, oh, and then what's the concavity? It's concave down and then concave up between the 2's. So I need to make sure I have concave up, and then over here I need to make sure I have concave down. Am I actually on the screen? I'm not. Okay, I'm writing little reminders for myself down here. I'm going to have concave down, concave up, and then 3, 4, I'm going to have concave down again. So concave down, so I'm going to be like, woo! I don't know where it starts, but I know that it hits somewhere nebulously up here, and then after -2, it's concave up. So but it's going to be concave up, crosses through 0, 3 until we hit 2. So it needs to keep on going. It still needs to be like concave up, but then we hit another, like, but it's going down. And then keeps going down and needs to be concave down. So there is my possible sketch of the graph. Okay, let's see what the next question says. Suppose that at any time t, the current in an alternating current circuit is I equals 2 cosine t plus 2 sine t. What is the peak, largest magnitude current for this circuit? Justify your response. Okay, so if I plug in 0, we wind up getting 2 times 1 plus 2 times 0. So if I plug in 0, I get 2. So I'm curious if we can ever get over 2. So what I'm going to do is I'm going to say I prime is equal to negative 2 sine t plus 2 cosine t, and we're going to say this is equal to 0. We're looking for our critical numbers. So I do that. So I didn't used to know this trick. I used to just kind of try to figure it out from here. But here's a trick that I learned. I add the 2 sine t to both sides. And now I divide both sides by cosine. And I divide both sides by 2 as well. And I get tangent of t. Sorry, I might have jumped too fast. Divide both sides by cosine. We wind up getting tangent of t is equal to 1. And so now we find the 4 values where tangent is equal to 1. And that happens to be at pi over 4. Oh no, it's not 4 values. Because 3 pi over 4, one's positive, one's negative. Pi over 4 or 5 pi over 4 are 2 possibilities. But I know I got a current of 2 when t equals 0. Let's see what happens when t equals pi over 4. So that's going to be 2 cosine pi over 4 plus 2 sine pi over 4, because I'm just trying to find out what are the actual values that I get out. So cosine and sine of pi over 4 are root 2 over 2. That's 2 root 2 over 2 plus 2 root 2 over 2. So we wind up getting 2 root 2. And with 5 pi over 4, I know the answer at this point. But it's worth talking about. Why give it away? So at 5 pi over 4, they're both negative. So we get negative 2 root 2 over 2 plus negative 2 root 2 over 2. So this gives us negative 2 root 2. So what is the peak, the largest current for this circuit possible? 2 root 2, because the square root of 2 is 1.4. So 2 times 1.4 is, 1.4 and then a bunch of stuff, but it's much more than 2. It's 0.8 more. So hope this was helpful. Feel free to spit out a message to me or, find me. I'd love to help you with any of this. Really, really good problems for us to be thinking about and working on. Have a great day.